Time. It is a constant companion. It never seems to stop or turn around. We are born, we grow older. This is a fundamental truth of our lives. We move from the past through the present towards an unknown future. This direction feels absolute, unbreakable. We remember things, a birthday party from childhood, the words someone spoke yesterday. These memories are traces of what has been. The past feels real, recorded, but the future, it is unwritten, a realm of possibilities, not memories we anticipate, we plan. This one-way journey is deeply ingrained in our language, in our thoughts. Once upon a time, stories begin, they unfold, they reach an end. Our lives are narratives, with a beginning, a middle, and an inevitable conclusion. This progression defines our existence. Let us begin to explore this arrow of time. Consider an egg. It falls from your hand. It shatters on the floor, a mess of yolk and shell. We never see the reverse. The pieces do not fly back together. The egg does not reform whole in your hand. This process has a clear direction, a one-way street. Think of an ice cube left on a warm plate. It slowly melts into a puddle of water. The puddle spreads, the ice cube vanishes. We do not expect the puddle to gather itself, to refreeze into a perfect cube, not without outside help, like a freezer. Spontaneously, this does not happen. These are everyday examples of what we call irreversible processes. A cup of tea cools down, smoke disperses into the air, a log burns to ash and smoke. The original state is lost. It transforms into something different, something more disordered, perhaps. The path back is blocked. They shape our understanding of the world. They tell us that time has a preferred direction. This is the arrow of time in action. Now, let us look at the laws of physics, the fundamental rules governing the universe. Consider Newton's laws of motion. They describe how objects move, how planets orbit stars. If you film a planet orbiting and play it backwards, it still looks like a valid orbit. The laws work equally well, forwards or backwards in time. Then there are Maxwell's equations, describing electricity and magnetism. Light, these two are time-symmetric, a light wave traveling one way or the other. The equations do not mind. Even in the strange world of quantum mechanics, the basic equation, Schrödinger's equation, it treats past and future symmetrically for an isolated quantum system. If the fundamental laws are time-symmetric, why is the world we experience so asymmetric in time? Why do eggs break but not unbreak? Why do ice cubes melt but not unmelt? The basic laws do not seem to forbid it. So, where does this arrow of time come from? It must arise from something else. This clash is at the heart of understanding time's direction. Scientists have a concept for this. It is called entropy. A word that sounds complicated, but the idea is quite simple. Entropy is a measure of disorder, or randomness, or multiplicity. The number of ways a system can be arranged without changing its overall appearance. Think of a tidy room versus a messy room. The second law of thermodynamics is key. It states that in an isolated system, total entropy tends to increase over time, or at best, stay the same. It does not spontaneously decrease. Things naturally go from order to disorder. Your tidy desk becomes cluttered, not the other way around on its own. This law gives time a direction. When an egg breaks, it becomes more disordered. The complex structure of the egg becomes a simpler, messier arrangement of molecules. Many more ways for the molecules to be in a puddle than neatly arranged in an egg. When ice melts, the ordered crystal structure becomes the more random motion of water molecules. Entropy increases. This is why these processes are irreversible. This increase in entropy, this natural tendency towards disorder. This is the most widely accepted explanation for the arrow of time we observe. Section 5, the quantum dance reversibility in the microscopic world. Let us shrink down to the world of atoms and particles, the quantum realm. Here, things behave strangely. Particles can be waves, and their properties can be uncertain until we measure them. The fundamental equation here, Schrödinger's equation, is time reversible for isolated systems. Imagine two particles colliding like tiny billiard balls. If you film this collision and play it backwards, it would still look like a valid quantum interaction. The laws governing these individual events do not inherently prefer one direction of time. At this very small scale, reversibility seems possible. However, the act of measurement in quantum mechanics, this is a point of debate. When we measure a quantum system, its wave-like possibilities collapse into a definite state. Some argue this collapse process is irreversible. It introduces an arrow. Others believe the collapse is an illusion arising from entanglement with the measuring device. The quantum dance might be reversible step by step, but the overall performance moves towards higher entropy. The arrow of time re-emerges. Section 6. Emergent time. Is time a fundamental ingredient of reality? We have seen that fundamental laws are time-symmetric, and entropy gives a statistical arrow. But what if time itself is not as fundamental as we think? Perhaps it is an emergent property, like wetness emerging from water molecules or temperature emerging from molecular motion. Individual molecules are not wet. A collection of them is. Some physicists propose that at the deepest level the universe might be timeless, no before or after in the equations. Time, as we know it, could emerge from more fundamental relationships, perhaps from quantum entanglement, the interconnectedness of quantum states, or from the very fabric of space-time in ways we do not yet fully grasp. This is a radical idea. It challenges our deepest intuitions. If time is emergent, then the flow we experience, the arrow of time, is a feature of our macroscopic classical world, a consequence of our particular perspective, our interaction with the universe. It is real for us, but not fundamental. These are theories at the cutting edge, exploring the nature of reality. Section 7. Cosmic Dawn, the Big Bang and the origin of time's direction. If entropy explains the arrow of time, why things move from order to disorder, we must ask another question. Why was the universe so ordered in the very beginning? For entropy to increase, it must have started low. This points us to the Big Bang, the birth of our universe. The early universe, some 13.8 billion years ago, was incredibly hot and dense, but remarkably, it was in a state of very low entropy, highly ordered in a gravitational sense. Matter was spread out very uniformly. This uniformity was a state of low gravitational entropy. As the universe expanded and cooled, gravity pulled matter together, forming stars, galaxies, and complex structures. This initial low entropy state is like a wound-up clock. The universe has been unwinding ever since, its entropy steadily increasing. This provides the grand cosmic arrow of time from which all other arrows derive. Section 8. The enigma of now, our perception and the deep mysteries of time. We have explored the physical basis for the arrow of time, entropy, the Big Bang's initial state. But what about our experience of time, the feeling of now, this fleeting, ever-present moment that separates the fixed past from the open future? Physics does not easily explain this now. The equations do not single out a special moment. Our perception of time's flow is deeply connected to our consciousness. Our brains process information sequentially. We build memories, we anticipate. This creates a subjective sense of passage. Is this flow a feature of the mind, or a feature of the world itself, or perhaps an interaction between the two? The now feels so real, so immediate. The mystery of time is not just about physics, it is about our place in the universe, how we, as conscious beings, experience reality. The arrow of time allows for cause and effect, for learning, for evolution, for the very possibility of life as we know it. The arrow of time points forward, and so does our quest to understand it. The journey into time's mystery continues.